This is a joint work with Stefan from TU Munich and my advisor Gerhard from Max Planck Informatics. So, this is roughly going to be the outline of this talk. So, online communities are dynamic in nature. As users join and leave, they adapt to evolving trends and adopt vocabulary, and then they mature over time. So, the focus of our research study is to find out how to capture this evolving user maturity over time in any online community. So, to give you an illustrative example, consider these following camera reviews by a user John. So, by reading the reviews, you can figure out when he joined the community in the year 97, he was not an experienced user in handling DSLR cameras. However, a decade later, he was quite mature in, he was quite an expert photographer and also matured in handling DSLR cameras, as you can quite figure out from his writing style in this given review, where he outlined the different fine-grained facets of the camera in vivid details. So, our focus is to find out how this user evolution occurred in the community, how did he gain his maturity and expertise over time. So, we have a closed world assumption. We do not consider how other users could have influenced this user via interactions, or how external knowledge, world knowledge could have influenced his expertise. What we claim is that this experience evolution is actually manifested in the writing style of the user in the community. To give you another example, consider the following reviews by the user on beer. And similarly, you can also see for the first review itself, the user focuses on many fine-grained facets of the item, whereas the second one is a very shallow one. So, the research questions we want to focus is how can we quantify this change in the user maturity that we refer to as experience in this work, and how can we model this evolution or progression in maturity. So, there are multiple use cases. So, assume that you have a model that can do this, then you can use it to recommend items to users based on their maturity to consume it. So, for instance, if you know that a user is an amateur photographer, then the DSLR camera that you would recommend to him would be very different from the one that you would recommend to a very expert photographer. Then also you can use it to identify experts in other communities, for example, maybe medical professionals in health communities, or for different crowdsourcing applications for rating aggregation and for community question answering forums, etc. So, there has been two prior works in this domain. The first work by Macaulay and Leskovich, it considers that users at similar levels of experience would have similar rating behavior and facet preferences. For example, in a beer community, expert users would like hoppy beers, or maybe experienced cineasts in case of movie reviews would prefer maybe complex narratives, maybe some kind of nonlinear narrative style of Christopher Nolan movies. We had a follow-up work where we say that the this expertise or experience progression is more manifested in the writing style of the user by the way he would write various reviews, as in the illustrative examples that I showed. Now, both of these works have significant drawback. So, both of these works model experience to be a latent variable that evolves over time. So, at each time point, a user either remains at the same level of experience or moves to the next level, thereby giving rise to this staircase kind of progression. And then you can observe that there is an abrupt transition. So, the user overnight switches levels. We want to model it more naturally as experience progression would occur in nature, that is continuously over time, something like this. So, this blue curve models the user continuously maturing over time in the community, and this we show is the continuous time or continuous state analog to the discrete version used in the earlier works. Now, as I said that the experience progression of the user is manifested by his writing style in the community, therefore, our assumptions about this expertise evolution strongly affects the language model as well. So, at the crux of the language model is a topic model, where a fundamental principle is exchangeability. So, the earlier work, so it assumes that as long as a user is at the same level of expertise, the documents that he would write are interchangeable, that is, the order does not matter. However, you observe that if you had a continuous scale of measuring the experience, then the writing style of the user would vary throughout his, even when he is at the same level of experience, especially when he is entering and when he is leaving that particular expertise level. We will also show it to be true when we show that in case you model the language perplexity, then it would give rise to a non-smooth behavior in case of the discrete model. So, in our current work, we wish to address both of these drawbacks and give you a continuous model of both experience and language model evolution of the user. Now, for the experience evolution, we have a few assumptions. So, this is how we think experience progresses naturally in nature. So, it should be a continuous time stochastic process and it should be always positive. So, we do not know what negative experience means. It should have a overall tendency to increase over time. However, the progression may not be completely smooth with occasional volatility. So, as a researcher, I may have a lot of top tier conferences, but then I will also have say second tier papers and workshop papers. But however, the trend is important whether I am improving myself or not. The other important thing is the Markovian assumption. So, the experience cannot switch abruptly overnight, or so there should be some smoothness in the behavior. So, the experience level cannot suddenly move from say 2.5 to 6.5 or come down to 0. So, we assume that the experience at any current or at any time instant should depend on the latest on the experience observed at the just previous time instant. Now, there can be many ways to model these assumptions. We show that there is a particular continuous time stochastic process that satisfies all of these properties, which is namely the geometric Brownian motion. So, the geometric Brownian motion has been previously used in the financial domain to model, for example, stock price behavior or any kind of financial instrument that evolves with Gaussian noise. So, we also show that so this geometric Brownian motion is a natural continuous state analog to the discrete state space hidden Markov model that I earlier showed, that is the one with the red color staircase progression. So, this is just summarized here. So, any process follows this geometric Brownian motion where the log of the random variable follows Brownian motion with the volatility and drift. So, I also explained why volatility and drift we think are important to model this experience progression. Okay. So, the geometric Brownian motion is given by the following stochastic differential equation having two components. The first one models the deterministic trend or the slope, and the second component captures the unpredictable events that can happen during the motion. So, it is very difficult to work with SDs directly in any computational model. Fortunately, we have a simpler analytic solution which mainly has three parameters. So, I need to know the starting experience value of a user, I need to know the trend and the volatility. So, these are three parameters which we learn from the data. Also, we fit one GBM trajectory per user. So, in a way this is a multivariate version of the geometric Brownian motion that we propose. So, for each user we learn the geometric Brownian motion trajectory, which has three parameters: the starting experience value, the mean and the volatility that we learn from the user specific data in the community. Okay. So, again to summarize, we are replacing this staircase kind of or the discrete version of the hidden Markov model with this continuous geometric Brownian motion process. So, now as we said that the user's experience is manifested in his writing style in the community. Therefore, the way the user's experience progresses in the community would also influence his writing style or language model, that is, it should also evolve continuously over time. Now, it should preserve a smoothness, so that the language model of a user cannot change overnight. So, I cannot every day pick up new words and I cannot change my writing style say every couple of days. So, it should preserve the Markov property where the language model of the user at any time should be depending on the language model at the previous time instant, but however the variance will change with the experience change between successive time points. So, if my experience is, if I am not progressing in the community, if my experience level is not changing, then my language model will remain almost the same. So, these couple of assumptions can be crisply modeled as follows. So, in the given example, this for example will say that the smell, hop, aroma, taste, etc., these are the certain facets, and the user here uses certain words to describe the facets, for example, grains, malts and etc. So, consider beta to be the language model which says which depicts the probability of observing a word W, say grains, that for a given facet Z, say smell, at any time t. So, my language model at time t depends on my language model at time t minus 1. However, the variance is dictated by the experience change between the successive time points. So, there can be several ways to model these. We just assume the principle of a standard dynamic system evolving with Gaussian noise, and then we can model it with the Brownian motion as follows. Okay. So, now experience and language model are continuous distributions, but in any generative process for generative model for actually generating the review documents, we need to draw the words from a discrete multinomial distribution. So, we need to have some way in which we can merge these continuous and discrete distributions during the generative process. Also, the language model does not evolve at the same resolution that experience will do. Language model will have a much coarser resolution, because as I said, I cannot pick up every word, new words every day, or my writing style just cannot change in 2 or 3 days, whereas experience evolves at a much finer resolution. So, we need to have some way in which we can consider both of these, and then we can smoothly and continuously merge the two distributions smoothly and continuously over time. So, the inference for our model is quite complex. So, for given a review like this, I need to understand what are the facets of interest. For example, smell, hop, taste, these are the facets which are not observed or latent. Once I know the facets, I need to know what are the words the user is using for those facets in order to learn the language model. Once I have done this, then I can infer the experience value of the user. The point to note here is that the facets are not observed or latent. The experience value is also not observed, that is latent. What I only observe are the words the user writes in the review at explicit time points. So, the entire process is quite complex. I will not go into details. This can roughly be summarized as follows. So, we start with a topic model. So, the facets are actually fine-grained realizations of the topics, in our case for items. We can add users to learn the preferences of the users for different facets. This is then similar to the author topic model. We add continuous make this facet model evolve continuously over time, which is again similar to the continuous time dynamic topic model. We then add our continuous experience progression with all the assumptions, and putting all of these things together is the generative model. That is a complex figure that is in the background. So, as I said, in the first step we want to estimate what are the latent facets. In order to do this, we can just use standard Gibbs sampling in the latent, as is used in this latent Dirichlet allocation model. While doing this, we assume that the language model and the experience that we have estimated from the earlier iteration to remain unchanged. In the next step, once we have learned the facets, we would want to know, learn the language model. Here the first equation then gives the normal, the sequential evolution of the language model beta, that is, it depends on the previous on the language model at the previous time instant, and the variance is dictated by the experience change between the time points. Once we have generated the language model, we would want to generate words for the review, which is drawn from a multinomial distribution. Here the function f is used as a transformation to move from the continuous to the discrete space. Now, again here we need some kind of inference technique to learn this sequential language model evolution, where we use Kalman filter. It is again a continuous state analog to the discrete state space hidden Markov model. So, once we have done both this process, we are now ready to estimate the experience. So, as we said that the language model at any time t, say beta t, will depend on the language model at time t minus 1. So, there is a link between beta t minus 1 and beta t, and then the language model would also depend on the experience change between successive time points. So, it would depend on et and et minus 1. Using this simpler Markov property, we can then derive a proposal distribution for metropolis systems, which is a kind of FMC sampling to infer the latent experience level of the user. This was truly a complex distribution, and we did not have any easier way of sampling, and then we had to resort to the complex to the slow and simpler metropolis testing sampling. Okay. So, we perform experiments in 5 communities. 2 of them are review beer review communities, Amazon Movies, Food for Yelp, and News Trust for news article reviews. So, there are a total of 1 million users with 500,000 items, 12 million ratings, longitudinally spanning over 10 to 16 years. So, for each we have a user ID, who is rating and reviewing a given item at a particular time instant. So, we have this quintuple that is the input to the model for each user. So, now first of all we show that the log likelihood of the continuous version of our model of the language model is much smoother than the one of the discrete version. This we again argued before that this is due to the exchangeability principle being violated in the discrete version. We can observe from the curves that our model converges very fast at around 50 iterations, then it becomes almost flat. So, it has a smooth behavior and it converges fast. Now, the question is, can we use this experience to recommend items better that we had earlier claimed? So, once you have estimated the language model and the experience value, you can use it for any standard recommendation task, for example, predicting item ratings. So, there the task would be to minimize the mean squared error of the predicted ratings with the observed ratings. You can use the language model and the learned experience value as features in the model. And then we compare with several state of the art methods for rating prediction, starting from latent factor models or models based on collaborative filtering, including our earlier works on discrete model and McCall and Leskovitz's work, etc. So, the lower the mean square error of any model, the better. The first one is our model with the blue column, and we show that it performs better than all of the other models on item rating prediction when we consider user experience, continuous user experience. Okay. So, from this experience progression or this geometric Brownian motion trajectory, we can have some interesting insights. For example, we see that experienced users progress much faster than the amateurs, but they also exhibit a comparatively higher variance. We also see that the progression depends more on the time spent by a user in the community than on activity, which means if I write a large number of reviews in a span of a few days, my experience will not progress that much if I write it over a considerable period of time in the community. We can also use this model to find out what are the evolving norms and conventions in the community. For example, how are different words used by users at different levels of experience. So, for example, these are two typical words, smell and aroma. Usage of each of these words increased over time. However, we can see that their evolution path is different. So, one is preferred more by the experienced users and gradually replaced. The other convention was replaced. Now, we wish to offer some interpretability in terms of what are the top words that are used by experienced users in different communities. So, that is also an outcome of our model. So, as you can see, for example, in the beer community, experienced users use more fruity words to describe a beer taste as opposed to the amateurs. In case of the news communities, you see that the expert users focus more on the government policies and actions and foreign relations, etc., as opposed to the non-experts who would be more inclined to debate about polarized topics. You may wonder that our model is only picking up rare words. It is not actually true, because for example, for beer advocate you see mouthfeel, or for Amazon seamless retrospect. These are not really rare words, but these are just the words that are used by experts more in these individual communities. Okay, so finally, to wrap up, we propose a Brownian motion based stochastic model to model the continuous evolution of user experience and his evolving writing style in the community. We show that experienced users do have a distinctive writing style that matures over time, and we also show that the recommendation models can be improved by explicit consideration of this user experience progression in the community. Thanks, and now I am ready for questions.
Thank you for the talk. So often you would see, especially with communities with experts and non-experts, you'd see many people coming into the community and importing the speech, trying to mimic the speech patterns, the writing patterns, the words. They're usually the same words. They would see how they would write, and certainly for a non-expert, it might be difficult to realize whether this person is an expert or they're just mimicking the speech patterns.
Right.
So it seems to me, at least, that the system would also think of these users as experts, actually.
This is a very good question, actually. It is also similar to the herding behavior that you would also normally observe. Like, I am always trying to mimic the experts. So the thing is, if this behavior is over a short period of time or a long period of time.
So
if it is over a short period of time, then it will not really matter, like our model will not be affected. But if it is a long-term behavior, then obviously we would like misclassify them as experts.
okay, thank you.
I'm not sure if this is because I didn't follow some details, but I was wondering if you also account for the volume of text that each type of users produce in model.
The volume means the number of reviews that are, number
of reviews, the size of reviews in terms of.
No, we don't use them as features. So all of the feature vector, I mean, when we use it for the prediction task, these are all normalized. So we don't explicitly consider the number of reviews that are being written by each user as feature in the model, but obviously the number of posts per user would, like, you have more data per user, maybe the model will learn the parameters better. So in a way, it would really influence it.
So, but it will also introduce some kind of bias in the model?
For very frequent words that are being used?
Yes, yeah, because if you have more text from certain type of users, I expect that it will influence.
So the thing is, if certain words are used, okay.
No, I was just wondering if if it accounts somehow for this kind of issues.
All these distributions are actually normalized by the count. So just because, for example, say stop words, just because they are used a large number of times, they doesn't figure out in the top words that are used by the experienced users as such. So these would be normalized by the number of reviews when we consider these distributions. So directly it won't impact.
Yeah, thanks for the talk. If I understood correctly, you make the variance be proportional to the experience?
Experience change.
Yeah, so what's the intuition behind that? Like, why is it going to be more varied because your experience has changed? Is it because you're going to use the vocabulary of your non-expert words and expert words at the same time, or?
So the point is, if the experience does not change, then the language model, then my writing style is not actually evolving. So it should remain almost the same. But if I am progressing faster, since our assumption is that our experience progression is manifested in our writing style. So if I am evolving, I am picking up more community terms, I am picking up the norms and vocabulary, so the writing style would change. So that is a principal assumption behind the model.
And I have another question, a bit more technical. So you said that you're converging pretty fast in 50 iterations or so. I'm guessing you average your parameters over some number of iterations at some point after your burn-in. How long do you average for? Like, because your model, is it good because at this point it's good, or is it going to get better if you run it and average over more iterations?
So can you just repeat your question?
So for MCMC and GIP sampling, you have a burn-in phase at the start where you don't take into account your parameters, and after that you start averaging over your set of parameters that you have. Have you studied in any way how this average parameters are evolving as you use more and more iterations?
No, not really. So this is after the burning out phase. So we observed that, for example, after 20, 30 iterations, then we can typically keep the burning out phase very low. We need not set it to say in thousands, for that is normally many times done for the GIF samplers. In our case, like if we just set the burning phase to 20 or 30 and then we start averaging, then we typically converge at around 50 iterations.
Okay, so let's thank the speaker.